those of you guys just joining us, they were making sure they had their 1 page of notes from section 6.4, which is usually many pages of notes. But this year, we're just going to focus that you guys can actually find a dot product and not like have you go through, not all, but several applications of it. So as you guys talking, I believe it's pretty self-explanatory. It's time to now be quiet and focus. So we are in section 6.4, dot products. And we're trying to figure out how these guys work before we have our workday review day on 6.1, 6.2, 6.3, and 6.4a. All I have from 6.4 are these 2 little pages. That's all I've got. So you already took notes on this one. It was up for quite a while. We have our dot product formula that I'm going to write right over here. Actually, no, you have it in your notes. You guys tell me. First of all, it's not U times V. It's U dot V. Let's not say U times V. It's not foiling. It's not multiplication. The formula has multiplication. The formula has multiplication, but it's not like outright multiplication. Right? Paul, what's up? Paul, why are you talking? Well, we're taking notes right now. It's 6.3 at the very, very end. 6.3 at the very, very end. Just like we saw yesterday. So we were at the end of 6.3. I'm picking up right where we left off. We're at the end of 6.3 at slides 19 and 20 on the Jamboard. Andy, did you have a question, kid? Awesome. So let's go ahead and take the dot product. You guys tell me, what is U dot V? Ready, set, go. The formula you just wrote down in the big yellow box.
U1.
Okay. So if I was to go ahead and find the dot product of this guy, wait, are you doing vector arrows? Are we doing vector arrows? Sasha, are we doing vector arrows? When do we do vector arrows? Every time we see what? Natalie, help her out. When do we do vector arrows? Every time we see what? I's and J's will have it, but that's not the only time. Ryan Krikorian, when do we do vector arrows? Every time we see what? Mask on while you're thinking. Ryan Unin, Chris, mask on. When do we do vector arrows?
In order to represent a vector, like so that it's like you go this way and then you go that way, like to show which direction you're going.
Actually, these little arrows don't exactly show which direction. They're more of just like a, hey, this is a vector. And I need to say, hey, this is a vector. Like on a picture, the arrow would, but vector arrows, the notation just says, he's a vector, he's a vector. Natalie was right. I's and J's are vectors too. But how does the book show a vector that I can't handwrite, and so I put an arrow? Yeah, I thought you'd think of that one. Jackson, mask up, and then you can answer. When do we put vector arrows? What do they do that show me it's a vector, that show me I need to put arrows on top of it? Brendan, when do we do vector arrows? When it's bold. When it's bold. Remember, the book shows bold and I show vector arrow. Uh-oh. Have you guys been putting vector arrows in your homework and in your work? Ooh. Am I going to have to take off points because you're not putting vectors? Hey, look. There should be vector arrow, vector arrow, vector arrow, vector arrow. Where are the vector arrows? Otherwise, they're just letters. Vector arrow, vector arrow, vector arrow, vector arrow. Where are vector arrows? Nice, nice. Where are vector arrows? Vector arrow, vector arrow. Any lowercase letter denoting a vector or any initial and terminal points denoting a vector need to have vector arrows on top. Vector arrow, vector arrow, vector arrow. Anytime you see a bold letter. Yes. Vector arrow, vector arrow, vector arrow, vector arrow. Otherwise they're not vectors. Vector arrow, vector arrow, vector arrow.
Wait, when you're doing like 5 billion times V.
Now, C does not have a vector arrow. Why does C not have a vector arrow?
Coefficient.
It's like a, kind of, yeah, it's a coefficient. It's a constant. It's a, we would call it a scalar. It doesn't have a dimension to it. But do you also see how C is not bold? Some of you guys were telling me U's and V's are just constants also, but no, there's vectors. C is not, but all the other ones are. Struggle bus. So, wait a minute. Did you put your vector arrows in your formula for your dot product?
Yes.
Yes.
Did you put your vector arrow for U and V?
Yes.
Better question, are you doing it now?
Yeah.
Aha! Thank you. Thank you. Or a W, or Andy, if we had like a PQ and we were talking about a vector, like from P to Q, right? Like we would have to put a vector there also. But anytime we're talking about components, those are just constants. So we're not putting vector arrows above components. So we're putting vector arrows above anything that denotes a vector. Struggle bus. Okay, now that we're getting our vector arrows, now I can go ahead and say, let's solve. Question, what are we multiplying plus what are we multiplying? What goes first? U. Now, who is U1? Uh-oh. Who's U1? Not 3. Not an I. It wasn't bold, right? U1 is not a vector. U1 is just a quantity. So it's just 4. I just take the coefficient. And if you would rather, you could also think about this guy as 4, -2, right? Can't we write it in, vocab time? What's this guy called? Component form. And what's the I's and J's? Linear.
Linear form. Linear vector form.
Walker.
Magnitude form.
Pizza now discontinued from Costco.
What?
We never had those.
Feels good.
Discontinued. One type of pizza from Costco. It wasn't cheese and it wasn't pepperoni. Supreme. Otherwise known as combo, and as a long word, combination. I thought the locker thing would have done it, but it didn't work. All right. But yes. Linear combination. Let's put the whole thing together. What are the I's and J's called again? Yes. Natalie, what was the word you said? With I's and J's? That's the second word. This is like charades. That's the second word. What's the first word?
Linear.
Linear. Now put it all together.
Linear.
Woo! All right.
Would you like it?
Can we try again? And this time be amazing. So what kind of name? It's okay. We're learning. What kind of name is the side carrot? I'm sorry. I'm sorry. There are 2 different names. He was ready for this one. This form is called component form. No, they both have components. They both have horizontal, vertical, right? But the side caret is known as component form, and this one's known as linear combination form. So I'm going to point to a form, and you give me a name. Ready?
Linear combination.
Are we good?
Yes.
Coming back. So if we take the coefficients from either form, the horizontal coefficients or the horizontal components from either form, I'm going to be multiplying 4 by what? Yes. There's nothing in front of the I. There's still an I. There's still one I. It's not 0 I or else there'd be nothing there, right? It's one I. And then I take my vertical components from either form. What am I going to have? Double check. Is what Natalie said makes sense.
Yes.
Horizontal times horizontal plus vertical times vertical. Jackson, go.
Wait, wouldn't it be just positive one because?
Nope, it's a minus.
Are we looking at B? Oh yes, yeah, okay. Yeah.
You see it?
Yeah, that's it.
So we do the first plus the second second.
Okay, I told you.
So multiply the first plus multiply the second.
Got it.
Now this dot product, guys, he's used in lots of ways. If you want us to do chapter 6 for a whole other week, we can go explore all those ways. Or we could just say, he's an important guy, I'll learn how to solve him, and I'll know his name if he ever comes up again. Does that make sense? Cool. So we're learning his name, we're learning how to do him. And actually what's weird is that he does not result in a vector, he results in a number. He's what we call a scalar. The dot part is a special scalar. And if you want to explore all the different ways, not all, but some of the different ways he's used, have fun going deeper into 6.4 and 6.5 than we are doing this year. We'll talk about logistics in just a second. But right now we're just getting down. Oh! That's a thing? It's a thing. Vector multiplication? No, no, no. But the dot product is a thing. And it's taking the horizontal pieces and the vertical pieces and multiplying them and adding them together. Ryan Krikorian, go ahead.
I was just gonna say, let a sign when you put like the points as your answer. It takes a parentheses, but in notes it's like an inequality sign. So like 4, -2.
Oh, if you were writing it, now this isn't the answer, right? 6 is the answer. But if you were writing it in component form, I think you can use greater than less than. Guys, help us out real fast in WebAssign. To show components, can you use the greater than or less than from your keyboard, or do you need to go to CalcPad and get special grouping symbols?
Go to
I use
CalcPad.
It sounds like people are using CalcPad. I mean, you have 4 tries. You can try the greater than less than.
It got it right. It's confused with what that is. And what is it?
It's a special type of grouping symbol. So grouping symbols, you've learned like different grouping symbols in the past, right? You've learned those since early days. You had a new meaning for these this year or last year in interval notation. You've also seen braces, and now you're just being told like, hey, these are also a grouping symbol. So it doesn't have the meaning of greater than or less than. Instead it has the meaning of I'm a special type of grouping symbol, pretty much reserved for vectors. Yeah, good question. Good question. Okay, so you guys, solve for me, number 24. Can you handle it if it gets a little exciting?
Yeah.
Because are you giving every single piece vector arrows that should have it? Ready, set, play with the math, go.
Okay.
Think PEMDAS. Think PEMDAS with dot products. Play with the math. But keep your answers quiet and we'll see if we can all arrive at the same place. Take your time.
Yes, sir.
Take your time. Piece by piece, step by step. Do the first one. Separately, just do the second one. And try to subtract it. What numbers would you fill in where? Take each of the pieces. PEMDAS says start with grouping symbol. Do the first dot product. Do the second dot product. Do you see it? Fill in the pieces. You got numbers. It can be in I's and J's. It can be in components. I didn't keep on writing my components, but if I had, U could also have been written this way, V could have also been written this way, and that's how I would have gotten my numbers over there. Yeah, should just be one number at the end. So the first dot product is a number, the second dot product is a number, we subtract and we get a new number. I don't think 8's it. It's a little bit bigger and it might be a negative number. You guys agree?
-21. I
I don't think it's 21. I
Oh,
don't think it's negative. It is a negative and it is kind of big. Not big as in the circumference of the earth, but big as in, you know, higher than 10.
Oh yeah, I got -22. I just did like simple math kind of wrong.
Double check.
Oh, I put 3.
Did you get the same numbers I got?
Fix the yes.
What?
I got 3. So how do you know the
3.
I put 3.
Double check, double check, double check. The first times the first plus the second times the second. For V and U and then W and V. Double check, double check.
Yes, I got that, but when you subtract it, this is
Wait,
That's what I know.
Yeah.
I'm confused. Positive? What is a plus or minus?
Oh, let's double check. Plus. Right? That part is addition. Struggle bus. Those of you guys that did -20 and me that did all the mental math in my head. Why is -20 wrong?
Because you subtract -14, it's supposed to be.
Oh! A negative times a negative is a, or a subtraction of a negative is a. Oh! People that got 8. Struggle bus. Congratulations. Gold star, gold star, gold star.
Brendan got 8 for
I know, my mental math. I was trying to do too many things.
You said it was a negative. I thought I did it about negative.
I was thinking,
I was like looking at that. I was like looking at it. I was like,
I could have gotten that. I don't know.
So I looked at,
I didn't know where it was going.
I didn't see that.
just in case, alright, quiet down, quiet down, quiet down. Excellent job, everybody that got the positive 8.
Let's go.
However, notation. I am following the dot product when I say V1 U1 plus V2 U2, but remember what this means, right? Every time I'm talking about component form for some general ambiguous vector, I can always think about the horizontal component as like, they usually use the same letter with the subscript of 1 to be the first component or the horizontal component, and the second subscript of 2 to be the second component. So check it, where did we get these numbers for this guy? I said, who is V? There he is. I'm going to take horizontal, horizontal, -4 times 3, and then vertical, vertical, 2 times 3. And the exact same dealio would be down here, but you guys tell me what would be the formula for this dot product. Not the numbers, but what would be the formula for this dot product? W1, good.
W2.
No, V2.
V, yeah.
V1.
Yeah. It's first times first. Do you see it?
Plus W2, V2.
Plus second times second. So this is what the dot product says, right? The dot product says go ahead and think of first times, I'm going to do it this way. This is what I'm doing in algebra. First times first is what's happening here. First times first. And then we have second times second as far as horizontal components multiplied and vertical components multiplied. Does that make sense?
Yeah.
So double checking our W's. W1 horizontal component of W, horizontal of V, 3 times -4, and then -1 times 2. Ba-dum-bum-bum. And I didn't look at the formula to double check. It was a minus. Struggle bus. Or at least I did dot products in my head. Right, just not the minus. So yeah, proper answer is a positive 8. Now, if we were to, right now, go to WebAssign. If we were to, right now, go to WebAssign, which I'm going to talk about some logistics, etc. first. But do you guys notice, did you notice, anybody get that far? At the very bottom of homework, it randomly goes from being really hard to being really easy.
Yes, sir, Steve.
Maybe not easy, but I've put just a few 6.4 problems at the very end. I've put just a few 6.4 problems at the end. Because here's what I have decided to do. If you read the post on Google Classroom, you should already be well informed. Where are we stopping in chapter 6? 6.4a, which says, oh well, at least you see a dot product and that it's a thing. Oh well, at least you see a dot product and that's a thing. If you're curious as to how this is used for projections, for angles between vectors, for other things as well, feel free to have fun with looking at 6.4 further or 6.5 further, because we can bring trigonometry into complex numbers and there's a powerful application to that. But long story short, we're going to stop with dot products, and today is our test review work day. Why? Because I'm like, you know what? We got a little bit behind. This chapter can get really, 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 really heavy, and I'm not trying to have it be really, really heavy for you guys this year because I'm not sure we could handle it. So, coming on back, quick update. Everything should be good to go. As you guys are opening up things today, let me know if any deadlines and whatnot are not good to go. So what you need to do if you have not done already, didn't I already say just mark as done 6.5, right?
Yeah.
However, anybody see what else I want you to do? All right, turn in the full 6.4 and the full 6.5. Turn that in. Instead, I just grabbed a few 6.4 problems and added them into our last homework of the section of the chapter. Homework number 30. Is that okay?
Yes.
So we're turning in. Marking is done. It's worth no points. I made them both ungraded. Just get them out of your queue. Get them out of your Google Classroom. Mark is done, 32 and 31. Okay? And instead, I just stole the first few of the basics of dot products, and I added them in, if you guys didn't notice yet, to our final homework of the chapter, which is homework number 30. That's the one we're going to be troubleshooting a bit today. The test review has also been shortened to where you're only going up to 81 and you're skipping these guys at the end. So to that end, as you guys are maybe like getting a bit organized, what did we not do in 6.3? Did anybody realize they had to go past quite a few different pages in 6.3 to get to 6.4? Why are there all these, oh, actually that one's not. Anyway, what did we not do yet? We did the basics of vectors, we did the basics of vector diagrams, we did the basics of components versus linear combinations, and even things like unit vectors, which some of you didn't like how I wrote it yesterday, so I wrote it with different letters to make it match and to make things prettier, except those different letters would also need me to be talking about you down here. I just made it a generic V, but we didn't like that because, anyway. So I changed that up to make it a little bit easier for you. But what did we not do?
Applications.
Yeah, we didn't do word problems, right? So help me out real fast. You might be in WebAssign, you might not be. You might be in WebAssign, you might not be. But those of you that are, can you double check? Do you guys have any problems like the two that are listed on the screen? Okay. Let's talk about this. First of all, are your numbers the exact same as the ones up here?
No.
Ah, so let's get the idea with mine and then you guys apply it with yours. Sound good? Let's get the idea with mine, then you guys apply it with yours. These are some interesting applications of vectors because this one says, how many forces do I have? How many forces do I have?
3.
Interesting. That's a little bit harder than 2. But Noah, your idea from yesterday, how it's like put the vectors and then bring them over and then find the resultant is perfect as far as what we're really doing. But it's going to get a little bit harder if we have 3 instead of 2 because, well, Hey guys, does the length of my vectors matter? Does the length of a vector matter? Ryan, you say yes. How come?
Because isn't the length like the magnitude?
Yes. And isn't this one 75, whereas that one's a little bigger, 90, and that one's a little bit bigger, 120? Struggle bus. So, can anybody think of something that goes into 75 and 90 and 120 for me to scale this somewhat? Can anybody think of anything that goes into 75, 90, and 120?
5.
Yeah, I was thinking 15 might be the biggest. Isn't that the GCF of everything? Right? 15 goes into 75, what, 5 times? 15 goes into 90, 6 times? And 15 goes into 120, is that 8 times? Double check, double check. Is that good? Why am I thinking that? Can't I go out 5, out 6, out 8, and it's scaled? Does that make sense?
Yeah.
I don't need to do like 120 tick marks. I can do 5 15s, 6 15s, 8 15s. I can go by 15s with my tick marks. But then I also need to think about 30 degrees. So 30 degrees would be down here, right? 45 degrees. What's my other degree, guys? 120, isn't that like 30 past 90? Are we good so far? Are we okay? If we were trying to do this with geometry, you guys would need rulers, you would need protractors, because we would need to actually have like 5 inches, 6 inches, 8 inches at these perfect angles to actually be able to do or to solve this vector diagram on paper. If we were doing it with geometry, let's see if I can do it at least fairly accurately. I want to go out 5. Do you guys know what respectively means in math?
Like they all go at the same time.
Yeah, so the first goes with the, does that make sense? 75 is at 30. 90 is at, just some people sometimes have questions with what that means. The first with the first, second with the second, third with the third. So I could go out 1, 2, 3, 4, 5. Okay, there's my first vector. Then I could go out 1, 2, 3, 4, 5, 6. There's my second vector. Then I could go out, let's see, where's my 6 here? 7, 8. If you guys think about it, I'm actually using this idea of radial geometry. Like I'm thinking of radial lines, like a circle of 1, a circle of 2, a circle of... That's the way I can have the scaling be perfect. That's something we're going to talk about later on this year. So anyway, here's my other vector. But I need to add all these guys together. I need to add this guy together with this guy together with this guy. And Noah, do you remember what you said yesterday? How do I actually add vectors together? What do I need to do?
I do not remember.
You said something about shifting or moving one of the vectors. And then,
You shift one or two towards the others.
yeah. I need them to flow in and amongst each other, meaning I would need this exact vector to be right here. Because I would need u plus v plus, and then I would need this guy to come over, because I would need to put them head to tail so I can think of them all together. And then do you remember what that, you said it really well yesterday, do you remember what that final vector is called?
No, I don't remember.
Okay, check it out. Find the direction and magnitude of the, we can think like the net force, we can also think the resultant. That guy is from the very beginning to the very end. Now the problem is, geometrically, how do I solve this non-triangle? Do you guys notice? As soon as I put 3 vectors together, is this a triangle anymore? No, because it goes and then it changes and then it... No, this is a quadrilateral. It's an awkward... How do I solve that? Law of sines, law of cosines? I mean, I could maybe play with different things and I could think of, well, this would be a triangle, I guess, and I could solve for stuff, and then that would be a triangle maybe, and I could solve for stuff, and then that would be a triangle maybe, and then I could solve, I don't know, maybe. Maybe we could split it up like that. Or maybe we have to think about things like...
Whoa.
It's okay. I think it's okay. Just, take a breath. A cleansing breath. As we come back eventually. Struggle bus. Are you guys okay with at least saying something along the lines of the geometry would be tricky to solve for that red?
Yes.
Is that okay for us to say the geometry would be tricky? It's not even a triangle anymore?
Yes.
So if that's true, what makes the tricky geometry simpler? What form? What form makes the tricky geometry better? Just a hint, it has side carrots.
Component form.
There it is. Because component form says, forget the geometry. Component form says, hey you, don't you have an over and an up? Cool, I'm going to use you. Hey you, don't you have an over and an up? Cool, I'm going to put you next. Hey you, don't you have an over and a back? Cool, I'm going to use you. And if we take the over and the back, guess what we're going to get to? The over of the big one. And what if I take the up and the up and the up? What am I going to get? The up of the big one. Let's break it down into its pieces and go little bit by little bit of each of our different components. How do I do that? Well, I use some spiffy formulas. Cool kids, what are those formulas that we started off yesterday with that have like magnitudes and directions and sines and cosines? What were those again? Remember you were supposed to get it in your calculator? Do you remember? Yeah, but given direction, given magnitude. Sure. Remember, Despicable Me, they're going to give you, very commonly, with vectors, they're going to give you directions and they're going to give you magnitudes. But I don't want that. I don't want to deal with that geometry. I don't want to deal with that quadrilateral or even worse, and parallel lines and laws of craziness. I want to just think over, up, and put them all together. How do I solve for this? You have a formula. It's in your notes. What does A equal? What does B equal? But it's not magic. You also have stuff that you know about SOHCAHTOA. If worse comes to worse and you're taking a long time to find it. So, opposite? What's opposite? Who is the opposite? B. All over hypotenuse. Who's the hypotenuse? Magnitude. Good vocab. So if I want B, question, how do I get B by itself? What would it equal? Sine theta times magnitude. Why? Can't I just move that to the other side? It's not magic. It's just right triangle trigonometry. So B is equal to magnitude sine theta. Question, I'm going to use this guy for every single up of each of my vectors. What's A equal? Well, what's cosine equal, guys? Who's adjacent? Who's hypotenuse? So question, what's A going to equal if I get him by himself? Do you remember yesterday we were putting in like 30 sine whatever and 50 cosine whatever? Remember? Do we not have that written in our notes? What a bummer. All this work that we were doing yesterday of trying to see if we could plug into our calculator, do you remember how I took the components? How I made the components from the magnitudes and the directions? Do you remember? Careful. Ask yourself, am I focusing? If I am, I could learn. If I'm not, I'm kind of shooting myself in the foot. So magnitude, cosine, angle, magnitude, sine, angle. It's me breaking it down into its pieces so I don't have to worry about the crazy oblique triangle or quadrilateral or anything else formed by forces. I'm just going to break it down into its pieces and add them all up. Positives with positives, negatives with negatives. And if I have 3 or 4 or 10 or 20, I can deal with really complicated vector diagrams by breaking it down. So, what is this guy going to be? A grand culmination of, well, kiddos. Let's start with the first guy. The first guy, I think I made him black. The first guy, 75 pounds at 30 degrees. What's his horizontal component going to be?
75
What's his vertical going to be? You guys agree with Natalie?
Yes.
Then Ryan, pick it up and go for the next guy. What would be his components?
It would be 90 cosine 30.
Careful.
Oh wait, sorry. 90 cosine 45.
You see it at his angle?
Yeah, because it's yeah. And then the other one would be 90 sine of 45.
Of what?
45.
Does that make sense, everybody? Does that make sense? So then, Paul, finish this off. What's the last one?
First one is 135. 135 called
Oh, 120.
or 120.
Yeah.
So it's what's the degree?
For me.
Okay. 120 cos 120
Uh-huh.
and 120 sine 120.
And I could do this all stinking day long, guys, right? I could do it all day long. Now, what's going to happen when I put this in my calculator is some of these guys are positive, some of these guys are negative, some of these guys are positive, some of these guys are positives, but that's all going to happen in my calculator. So like going forward, going back. That's going to happen when there's a negative in the second quadrant. Going up, going up. That's going to happen. All I need to do is just add them all together. Right? When I add them all together for my resultant vector, I know my numbers are different than yours, but for my resultant vector, does it make sense I'm going to get an R1 and an R2? Does that make sense?
Yes.
I'm going to add them all up and get two numbers, right? Are those the two numbers that I put in my blanks?
No.
No, those are the components. So check it, kiddos. Look at my picture. Wouldn't my components give me R1 and R2? Do you guys agree?
Yes.
R1 and R2. What are they asking for in the boxes?
Add the whole left side.
Oh, so I need to go from these back.
Yeah.
How do I go back?
It's
Formulas. Yeah, what's going to allow me to take a leg and find a hypotenuse?
R1 squared plus
Oh, nice. That's totally a thing, right? Can't I do R1 squared plus R2 squared is equal to magnitude?
Yes.
Well, after you square root it, right?
Yes.
How am I going to find beta?
Inverse tan.
Inverse tan, which is a formula that you might have written down, or it's maybe something that you can just look at your formula and say, oh, I have opposite, I have adjacent, I'm going to use a tan inverse and go back. Do you guys want to try that one in your WebAssign right now and see if you can get it to match?
Yeah.
Not a bad idea. WebAssign open, go find it. What number is that in your homework, cool kids?
17.
Oh, 17, take it away. My numbers were different, but they're awful similar to yours. I'm going to go open the door. Is it the CalPV? Yeah. Here we go. A heavy object is pulled. That's cool. Some people hate it, but for others, you're like, oh, I can see it.
Except when you did that triangle thing, I don't know.
Or you did most of it.
Graph on the left. I don't know what gets there.
But the math makes sense?
Yeah, that makes sense. That does not.
But do you see how I'm doing like the little side, the little side, the little side?
No.
That's what I'm doing. Okay, so going back. A heavy object is pulled 30 feet across the floor using a force of 95 pounds. That's a magnitude, right, guys? The force is exerted at 50 degrees above the horizontal, and they gave me a nice picture, and we say, thank you. Hey, do they tell us something about work in this problem? Well, kids, they give us a formula for work. Did you realize that work is only done if something moves?
Yes.
Really? You all knew that? Work is only done if there is movement. I'm not saying you might not be sweating without movement, but work is only done, the definition, mathematical definition of work is only done if there is movement. I should say if there is distance covered. So if I'm trying to say work is equal to force times distance, oh my goodness. Where F is, okay, check it. Things have gotten more complicated than 8th grade science. Where F is the component of the force in the direction of motion. F is the component of the force in the direction of motion. This thing is heavy. You have a rope tied around it. You're trying to drag with the rope to get some extra leverage. So I'm exerting force at an angle. The question, am I allowed to just take 95 and plug it in my formula? Yes or no? According to what we just read. Am I allowed to just plug in 95 and say 95 times 30 and I'm done? No. Why not though? It says F is the component of the force. Wait, when it says component, what should I be thinking? Yeah, maybe like a piece of it. Maybe it's not all of it. Component, like, hey, I could break this down into different pieces. The component of the force in the direction of the motion. Guys, is the box coming up along my shoulder? Is the box moving this way?
Yes.
What does it say in the words? Is being pulled where?
30 feet across the floor.
Oh, so where is the box going? Is it going up in the air? No. I'm pulling, and what's the box doing?
Across the ground.
Dragging across the ground. So where is the motion of the box? This way. Yeah. So wait a minute. How on earth can I figure out what the force is, what my pull is accomplishing here? How can I take this and figure out that?
120 cosine 50 degrees.
I can think of exactly, this force is not just what it appears to be. This force is not just the 50 degrees that it's at and the 95 pounds that I'm exerting. I can also break this down into its components and say, what does that mean down here? Or I could also talk about it in terms of its vertical components. I could talk about what it's accomplishing down here. I could talk about what it's accomplishing up here. But technically, according to what they said, I only want this one. Because I only want, for my work formula, I only want in the direction of the motion of the box. The box isn't going up. The box is going over. Now, why did somebody just say cosine? Cosine, look, cosine finds the adjacent, right? Cosine finds the one at the bottom. So therefore, I am going to go ahead and say, who are you in the x direction? I could be super snazzy and say force, like the horizontal force. I could talk about it that way. I could also name it A. I could also name it F1 for F1, F2 in the component form. But I'm going to do magnitude, cosine, angle is my force in the direction of the motion. And all of a sudden, I have actually, as long as something is being dragged across the ground, I have a formula for work every time. Because I can just say, hey, it's the magnitude of the force at an angle times cosine of the angle at which it's being exerted times the distance. But that's only if something's dragging across the ground. What if I was hoisting something up? I don't know how you'd be hoisting something up at an angle, but either way. For other problems, it might be moving in the same way that I'm pulling, like if I'm pulling it up a slope or a slant. But if I'm just dragging it across the ground, this is what I'm always going to have as far as that's how I solve. I can go ahead and plug and chug, and I will have my final answer. For me, it would be 95 cosine of, what's my angle? 50 degrees. Times how far I go is 30 feet. And it also gives me hints as far as units. It says foot-pounds is what this work is being measured in. The feet come from here. The pounds of force are coming from there. So everything's going to work out perfectly with units as well. But that's how mine would be done. You guys go and apply it to number 19 if you have not yet. You guys go and apply that to number 19 if you have not yet. But they said I need the force and how it's working with the object, not just where it's being exerted, but what that means for the object itself. Number 9, wasn't it 19? It's 20? 20, sorry. Number 20. I don't know. You guys are just shouting out numbers. I figured you could make it match. Hey, do you have one with something on a slope or a hill or a slant?
think I did.
But I was on it.
Okay. No, I'm just trying to help, like, if it would be helpful. If it's not, I'm assuming it would be helpful.
See, how do you get a direction?
You already got it. Natalie, what?
How do you get a direction?
Ryan, you can go ahead and go Google Classroom and work on your test review button. We're just having a work period for whatever we can use it on. Direction angle? Do you see how the bottom formula with tangent says give me the components and I'll give you an angle with tangent inverse? That's probably what you want to do. So I could use like my
Tangent -1.
or R2 over R1.
Yeah, you have the components.
Be careful though. You might need to draw a picture and ask yourself what quadrant. Because tangent inverse will only get me to somewhere here or somewhere here. Because tangent inverse is restricted to only negative 90 to 90. So let's say your picture has the resultant over here. Then you would need to take your angle and add 180 to get the actual proper angle.
Is the resultant,
The resultant is the red one. Like, where are you at the very end of all this? Or you can take your X and Y and ask yourself what quadrant. You can do that too. Or your A and B. All right, if you guys have a slanty one, you're bound to have a slanty one. I had to give you one on an inclined plane. What problem gives you one on an inclined plane, guys? Oh, I didn't give you one on a slope or on a hill or on a plane?
No.
Interesting. I'm only saying interesting. Okay. I'm going to take this dude and I'm going to blow him up. Not literally. Okay, here's my ramp. Here's my incline. Cool kids, remember last time? We had a troubleshooting day. Then I had emails and lots of complaints about how no one felt ready for anything, and I was like, man, I wish they'd paid attention on the troubleshooting day, because all he was trying to do was answer lots of questions. A few of you guys are not taking advantage of this time. Some of you are. Some of you are not. Just a recalibration of where am I? How am I doing? Am I using this time productively? Okay? If I have some sort of object on any sort of incline, there are some forces at play. The forces at play is I have one that goes straight down. I'm not sure exactly what the number quantity is, so I'm just doing some generic straight down. I have one that's called the normal force or the perpendicular force to the surface, which you kind of saw in the roller coaster example. You have a force of the object against the ground. If you were like a little mouse underneath this box, you'd be squished. There is force against the ground, but there's also force straight down. And then I have this little guy also right over here. Okay. When they're talking about these different forces, if you guys notice, one of them that they're saying right here is the force required to pull. I am highlighting that in red, because if you were pulling it, that's how much or how hard you would have to pull in this direction. I think about the direction of the force. It would be up here, true, but then I can move that vector down. The force required to pull is that red one. The combined weight of the boat and the trailer would be this green one. The combined weight of the boat and the trailer would be that green one. And then we kind of have like this other ambiguous one that we don't normally talk about that we could call like the normal force if we wanted. We could also call that like the normal force. It's also known as the perpendicular force. So we have the weight right over here. We have the normal force over there. And then something about the pulling force is this guy down here. Now, if we were to take this little baby right triangle and I was trying to sort of blow him up. It's just a right triangle. That being the green guy, this being the red guy, and this being the blue guy. And we can plug in a few things. However, there is one other extra that I didn't even say and I should have. And I would have to do a lot of geometry to kind of show you how this works, but I could get some parallel lines going. Eventually, we would be able to show that this guy this little triangle, actually has right up here the exact same angle within it of all these different forces as the original incline itself. So I know it's weird because the incline is way over here. But with geometry, we'd have to get a lot of work done as far as why it's true. But eventually we would get that this little triangle that all the forces make would have that little inclination right up there. Now this is technically, to be honest, one of the trickiest problems in the sense of I really easily mix up which of these forces are which. So I haven't done a lot of physics in a while. Let me double check that I've labeled everything right. I think I have it. The combined weight is BA. Because weight is dependent on gravity, and gravity says I take them straight down. So as a result, if I want to talk about, well, I can talk about a few different things, but if I want to talk about the weight, there's the normal force. Oh, wait, I labeled the wrong one. The weight, the normal force, and the pulling force. I could label all my different pieces. Like, the pulling force, they told me is 600. I'm like, okay, cool. And then they tell me that it's 15 degrees. And I say, okay, cool. So I have 600 for my pulling force. I have 15 degrees for my inclination. And what they're asking for is find the combined weight. What they want is the magnitude of this guy. So we just have to think trigonometry, but the picture is crucial, and without the picture, it would be so confusing as far as what is what. Weight is that little guy, the hypotenuse. Weight is the force of gravity straight down, or is combined with the force of gravity. But guys, if I just look at the triangle, I have a theta. What side is 600 if it's over here from the theta? Opposite, adjacent, or hypotenuse?
Opposite.
Uh-huh. And then what side is this one that I'm trying to solve for or find? Hypotenuse. And so what on earth says, I'll take opposite, I'll take hypotenuse, and I'll put it all together?
Side.
Which one says, I'll take opposite, and I'll take hypotenuse, and I'll put it all together?
Side. Side.
Exactly.
Oh, wait.
Misty, does the 600 pounds always go like on the bottom, like going towards like?
Well, only if it's the pulling force.
Oh.
It can either be like what force is required to pull it up, or it could also be what force is required to hold it. It's that idea of whatever tension is being given to the boat in that parallel fashion. Do you see it like parallel to that little vector diagram? What force is being given to it along the actual slant itself? Because gravity says straight down. And that poor little mouse that's squished is like, ooh, and it's also perpendicular. And then this guy says, I'm giving force along the actual slope.
With the when the boat's in the water, you don't need 600 pounds to pull it, right?
I mean, if it was actually floating, but do you see how, I mean, I guess this does show like a little bit of it in the water, but right now, I think it's meant to be only the wheels in the water. So the boat has no flotation. But yeah, it would be very different if it starts to float, right? Yeah. Not to say that couldn't be modeled, but that's a bit above our expertise right now. But yeah, you're thinking that there would have to be a lot more at play. So when we're solving for this one, we could just say, hey, this little weight guy is just going to be 600 sine of 15. And that's for mine. So can you guys apply that to your number 19 because you have something on an incline? I think so. Check it out and see if it helps. For those of you guys that are in that WebAssign, are there any of those nasty word problems that I haven't helped out with yet? Okay, I'm going to freeze the screen so that people can use this on 19 and let me go see what's going on in 16. I have some other examples, but I want to be... If he's throwing at 37 down, I don't label it with 37. What do I label it with?
Negative 37.
Exactly. It's going to be a negative 37. And then when it says the how fast, that's not telling me the horizontal component or the vertical component. That's telling me how fast he's throwing it in this line at this direction. That is my magnitude. So then they ask me, okay, if that's what you know it is, then go ahead and break it down into its components. And so, kiddos, that's just that nice little magnitude cosine angle, magnitude sine angle. You're just trying to find what is the A and what is the B to this situation. You're right back over there with our cosine angle, sine angle, but you should be using negative 37, right? Andy? Yeah, go ahead. So then, once we get you guys through number 16, which was a basic, like, horizontal, vertical component question, quick word to the wise. Remember, I do have TAs checking work. I see a lot of you just throwing in answers. That's dangerous. And not only is it dangerous for your grade as far as showing work, but it's also dangerous for your brain retention, for your memory retention, if you're not actually making your brain write out these steps and remember these formulas. That's dangerous, cool kids. I'm not trying to beat you down. I'm just trying to help as much as I can. And in my experience, getting a quick green check mark does not help you retain information. It just gives you affirmation that you're on the right track, but actually showing that work, writing down the formulas, processing what you're doing, that helps you retain. I have a tension problem, and I think this tension problem is pretty close to one of your problems too. Do you guys have something kind of like this with a tugboat or with something? It's exactly this one.
It's 4,000.
The numbers are a little different. Cool. So let me help with this one. Is that cool?
Yes.
Okay, with the tugboat there? A letter barge is being towed by 2 tugboats, and the magnitude, vocab, of the resultant is 6,000 pounds. So they're saying both these tugboats, which maybe wouldn't have been able to pull it on their own, but together they can. The overall result is that they are dragging this guy at a force of 6,000 pounds along the axis of the barge. So somehow they're getting it to move, and to get it to move, that means that they must be combining to get this 6,000 pounds of force along that axis. Now they say find the tension. Oh, hey guys, careful. Homework isn't just to practice. Sometimes homework is to learn. Did you guys already hear today that we learned a little bit about work through a problem because they were trying to guide us as to what work is and how it's found? And then in this problem, they're also introducing us to something else. And what's that something else that you wouldn't have seen otherwise? Tension is another application of magnitude. How fast, how far, how strong. How strong could be a force. But another way of saying that could also be a tension. Okay, so we have a new word, tension, still magnitude though. Find the tension in the tow lines when they each make an 18-degree angle with the axis of the barge. So what they're asking is, what's going on, making sure I still have a good marker, for the tension of barge 1 and the tension of barge 2. Now, they're both at the exact same angle, so we can kind of assume that the tension is the same on both lines. But we still have to somehow set up this situation. So, okay, hold on. If I were to think about this in terms of right triangles, I could draw my situation. Is that good, huh? I could draw this situation with 18 degrees here. I don't know this guy, I don't know that guy, but I do know this guy is 6,000. I know 18 above, I know 18 below, and I know the overall guy is 6,000. Wait a minute.
You got the adjacent on both sides.
Yeah, I have the adjacent. And I have the angle. Hey guys, just a little bit ago when I had like the opposite and an angle, wasn't I able to find the hypotenuse?
Yes.
So maybe if I have the adjacent and the angle, I can find the hypotenuse as well?
Yeah.
So if we just label this guy and say, oh, I see, he's the adjacent. Whether I'm looking for x or whether I'm looking for y, whether I'm looking for x or whether I'm looking for y, will it work if I just say cosine of 18 degrees is equal to adjacent over, for instance, hypotenuse? What do you guys think? Could I just say it's a basic right triangle, I have the adjacent, I have the angle, let me solve for the hypotenuse? You would think so, right? From the way I drew the picture, down here as well. But there is a slight dilemma. Do you know what the slight dilemma is? What was different in this picture than this picture?
There was only one.
Yeah, exactly. There was only one triangle here. And I knew the definite amounts of how they came together based on just how the forces work with something on an incline. That I showed you, and then you guys were able to use that as well. This one has two barges, two tugboats working together. So do you want to see the assumption I just made that made you all think this was easier than it actually is? The assumption comes all the way back in how I did my triangle. Question. Did they ever tell me, or did they ever show me just how long 6,000 is in context of this problem? Do they have anything showing me just how long 6,000 is? And all of a sudden I'm in some trouble. How long is 6,000 compared with how much those barges are pulling? I don't know. I don't know how much the barges are pulling, so I can't totally make the picture. So even if I come down here, 6,000 is like this bigger one. I don't know how hard or how far or how long to make the barges. So all of a sudden it's like, well, that picture would have been great if the 6,000 was here. But that's saying each one was pulling 6,000, which they're not. They're combining. Vectors.
So why don't you just go 3,000? I know.
The two barges are combining to make the 6,000. The two barges, when I combine forces or vectors, I'm adding. This is talking about a resultant. They're telling me what's at the end of this situation. They're saying, like, hey, as they pull together, this guy, well, hold on. I do know that he's going horizontally. 6,000 is his horizontal component, and 0 is his vertical component because he's being pulled straight into harbor. So I know what happens when both my tugboats are combining to make this overall effect. And so we're going to actually work our way backwards as far as a resultant problem, and we're going to say, hey, this is our overall result. This is what happens when I add together my two different little vectors. Or I should say my two little different tugboats. So if I think about my tugboat 1, if I think about my little tugboat 2, and it's like, I don't know your magnitude, cosine 18. I don't know. Ooh, I need to put a comma, not a plus. I don't know your horizontal component. I don't know your vertical component. But I do know that you are joining together with this other guy. Some of you might assume that the tugboats are pulling the exact same, once again, with that exact same angle, so maybe you would just put X's all over the place. To be safe, I would say we probably should just give them two separate magnitudes. And so now what we technically have is, if we were to say like, hey, let's add all together, we have this 50 system of equations where we say x cosine 18 plus y cosine 18 is equal to 6,000. If I add horizontal plus horizontal, I get that guy. And if I add vertical plus, need the x in front of that guy. The vertical of the first. And the vertical of the second. Now the nice thing for you guys, isn't this one of the step-by-step ones you just get to follow in your homework? Isn't this one of the step-by-step ones in your homework?
Yeah.
Yeah, I think so. So I did give what I thought was one of the trickiest ones as far as like you don't know that guy or that guy and you need to combine them in order to get the overall result. I gave it to you as a step-by-step so that you could be led along this process or this path. But if they were pulling at different magnitudes, this would be able to solve for it because I could go ahead and do a little bit of like substitution and plugging in. Now once again, I know some of you are like, oh, let's just make them all X, and I hear you. But just showing you the general idea that we could use for other problems as well if they weren't the exact same. Trying to show you how we could say, hey, the combined effect is the resultant, which comes from adding together the separate pieces, and that would form a system of equations that I could go ahead and, I see you, Brandon, hold on. I could go ahead and solve for one variable in terms of the other variable, and I could go ahead and plug that in and solve. What's nice, though, is once again, they do end up being the exact same thing, except one says I'm pulling to the right and up, and the other says I'm pulling to the right and down. They're almost the same, except one has a positive vertical component, the other has a negative vertical component, just based on the direction of how it's pulling. So I could go ahead and say, oh, hey, I know who you are. And I could plug in and I could solve. Brandon, what's your question?
For the B2, does it matter if it's cosine negative 18 and sine negative 18?
Oh, I was just saying angle to in a positive way. No, you're totally right. I should have put that negative angle. I mentioned it and then I never put it, did I? And he's seeing that once again is in reference to the motion. So that second barge is pulling down. And that would have been a negative. But with the even odd property, technically it ends up being the same thing. Because if you think about the odd property, sine of the negative is negative sine. So these would still reduce with the same angle. You know what I mean? So technically those would still reduce with the same angle, the negative going away. I'd still have that same relationship. So it's actually not going to change up. Oh, I labeled the wrong ones. Never mind. I need y, this guy to be a negative. There we go. That guy to be a negative. So then that would be a positive with the even odd property. Because that sign would be the opposite when you pull it out. There you go. So I'm just playing. I know most of you guys are working on different problems or you were able to follow the step-by-step. I'm just going to finish up this guy so you have it in the Jamboard. So it's technically our last example, if it would be helpful. Go ahead and pull out that x from cosine of positive 18. Plus cosine of negative 18.
How much work did you show for this? Oh, Insane, bro.
Yes,
So much going on here too.
Coming, give me 1 sec. I made this guy Y. And I made this guy X. And Brandon, they both end up being the same, like positive, because it's the hypotenuse, which is always positive, right? So I won't have to worry about the different directions because it's that absolute value. Right, what's up, bud?
How did you get X and Y?